Good day everyone, this is Mr. Fugay, and in this video we are going to look through a few additional examples of how we can use the first derivative to identify increasing and decreasing intervals as well as relative extrema. So here's the first example that we had done in class today for those who were in class. In terms of finding the steps here for this, this is earlier on in the notes, but just to recap, we want to locate all critical numbers, and critical numbers are where the derivative is equal to 0 or undefined. We will then identify those changing points. We will then determine the sign of the derivative in between those intervals of the critical points, and then we can decide whether it is increasing or decreasing across that interval. So we're going to look at our next example, and I'm actually going to change this example because this was more of the same of what we had done in the first one. So the new example that I'm going to have you guys write down here is x cubed plus 6x squared minus 36x plus 10. And so the first step, as we did in the last problem here, is we're going to take the derivative of this first because we need to identify intervals where it is increasing and decreasing. So we're going to look for critical numbers. So there's my derivative. We're going to go ahead and set that derivative equal to 0. And we're going to solve this. So what I can do is I can factor a 3 out. And what that's going to leave me on the inside here, and I'm actually just going to skip ahead, that's going to become x squared plus 4x minus 12. And so when I factor that, we're going to get x and x. We get plus 6. We're going to get minus 2. And so when I solve each of these, we're going to get x equal negative 6. X is equal to 2. And these are going to be my two critical points. So what we're going to do is we're going to create a sign chart. And keep in mind that a sign chart is not a justification. It is merely a graphical way or visual way for you to understand where the intervals of this are happening. So we have 3 different regions we need to test. We have to look at all the x values lower than negative 6, the x values between negative 6 and 2, and the x values bigger than 2. So again, the way that we're going to do this is we're going to choose any number we want inside of this yellow interval, and we are going to check its sign. That's all we have to look at is the sign of the derivative in that region. So I'll choose the number negative 7. So when I do that, if I go ahead and I use the first derivative here, I would get 3 times negative 7 plus 6 is a negative number. Again, I only care about the sign. Negative 7 minus 2 is also a negative number. Negative times a negative times positive 3 is a positive slope. So that first region will be positive. My next region, I'm going to go ahead and choose, I love picking 0 when I have the ability to. So we're going to get 3 times 0 plus 6 is a positive. 0 minus 2 is a negative. So we have 3 times a positive times a negative. So the sign is negative in this middle section. And then the last region, I'll choose the number 3. So we'll get 3. 3 plus 6 is 9. 3 minus 2 is 1. So those are all positive values. And so we're going to get positive, negative, positive. So what this tells me is that we're going to be increasing, then decreasing, decreasing, then increasing. So in terms of coming up with my intervals, so let's talk about increasing and decreasing intervals first. We are increasing from negative infinity to 6, to negative 6. That's going to be a closed. And then it's going to be from positive 2 to infinity. So keep in mind that the definition of increasing says if the derivative is positive on an open interval, then it is increasing on the closed interval. So that's the reason why we're using brackets and not parentheses. And then the decreasing interval is going to be from negative 6 to negative 2. So there's my decreasing and increasing. And then the last thing we need to do is we need a relative max and we need a relative min. And so in this situation, we're going to have a relative max at x equals negative 6 and a relative min at x equals 2. So there are going to be all my solutions for this second example. I'm going to have you take a moment and try this example on your own. So please go ahead and pause this video to try to do this. The solving of the derivative might be tricky because we have to use some trigonometry, but besides that, it should be fairly straightforward, similar to the problem we just did. So pause this video for that now. All right, welcome back, and here is my work. So we went ahead and we started by taking the derivative here as the first step, and that's going to be root 3 cosine x minus sine x. We set it equal to 0, and this is where things get tricky. If you have a calculator, obviously you could have solved this pretty quickly, but let's talk about how we would do this without a calculator. The easiest way I would recommend doing this is taking this negative sign, moving it to the other side, and having sine of x equal to root 3 cosine of x. Now that root 3 is kind of important because we're basically trying to come up now, is there an angle whose cosine ratio, when you multiply it by root 3, will equal its sine ratio. Well, as soon as I see square root of 3, I immediately think the 30, 60, 90 triangle. So I drew my 30, 60, 90 triangle out here, and I say, well, if cosine of 60 is 1/2, which is true, if I multiply cosine of 60 by root 3, I would get root 3 over 2, which just so happens to be sine of 60. So I really was looking at the relationship between this root 3 here in terms of coming up with my answer. So I knew that cosine of 60 was 1/2, and I knew sine of 60 was root 3 over 2, and they both happen to be a difference of a scalar factor of root 3. So it appears to me that our answer here that we're getting is pi over 3. So that gives me my first answer. But then the other answer we've got to consider is other quadrants. So quadrant 2 and 4 would be out of the running because one would be positive, one would be negative, meaning sine is positive in quadrant 2, cosine is negative. So that's why quadrant 2 is out of the running. And quadrant 4 is out of the running for the exact opposite reason. However, in quadrant 3, sine and cosine are both negative, so this same relationship would apply, and so 4 pi over 3 would be my other correct answer here. Now from this point, we're going to go ahead and move it over here to the open interval from 0 to 2 pi. Notice I did put those endpoints on here just to make sure to acknowledge that we were only looking at that interval. So with doing that, and I checking my sign values out here, we're going to go positive, then negative, then positive. So I didn't write this down, but the maximum would occur here at pi over 3, and that should be a relative max, that is. Relative min is occurring at 4 pi over 3. So here's my increasing, decreasing intervals. So we would be increasing from 0 to pi over 3. And we would also be increasing from 4 pi over 3 to 2 pi. And then my internal interval here with the decreasing is going to be pi over 3 to 4 pi over 3. Last but not least, we're going to have a relative max at pi over 3. And we're going to have a relative minimum at 4 pi over 3. And so there's all my work for this next example. And to wrap up this video, I'm going to do a bonus example with you that is not in your notes, but we're going to go ahead and check this one out because this has something different that the first 3 examples have not shown us here so far. So the example that we're going to look at in this last problem here is the following. We're going to do 9 parentheses x squared minus 1 raised to the 2/3. And so what we're going to do here is take its derivative. And when I do that, we're going to get 6 parentheses x squared minus 1 to the negative 1/3. Because this is chain rule, we're going to multiply by 2x. And when I clean up this derivative a little bit and just make it easier to read, it becomes 12x over x squared minus 1 to the positive 1/3. Now, what makes this derivative different than the other ones we've done is in the first 3 examples, we're just looking at when the derivative was equal to 0. And in this case, we will do the same. The derivative, when you have a rational function or a fraction, is going to be when the numerator is equal to 0. So if 12x is equal to 0, x equals 0 is going to be a critical point. But what we hadn't seen to this point yet is a time where the derivative is undefined. And since we have a denominator here, whenever the denominator is equal to 0, this would be a position where the derivative would be undefined. So graphically, this is a corner, a cusp, a vertical tangent, or something like that. So when we go ahead and we solve this, we're going to get actually 2 answers for this. We're going to get plus or minus 1. And so we're going to go ahead and do the same thing we've been doing with the other questions. We're going to create a sign chart, and we're going to evaluate that sign chart at these values. So we have 4 different regions this time that we have to look at. We have this yellow one, this blue region, this green region, and then lastly this pink region. So these are all going to be places where we have to look at. So again, looking at the derivative, I'll pick something like negative 2. And if I go to the original derivative up here, there's the derivative, I would get a negative number in the numerator. Negative 2 minus 1 is going to give me, negative 2 squared, first thing we got to do is positive. Positive, a big positive minus 1 is still positive, so it looks like we're going to have a positive denominator. So this first region is decreasing. In the next region, I'll pick something like negative 1/2. Up in the top, it's still going to be negative. But this time, the denominator is going to become negative. And the reason why is because after you square 1/2, you're going to get something small, minus 1, which keeps it negative. And when you take a cube root, not square root, a cube root, that's going to make it negative. So that means in this blue region, we're going to have a positive answer. We'll continue to do this for the other regions. And for positive 1/2, we'll now have a positive numerator. We'll still have that negative denominator. So we'll have a negative region here. And finally, if I test something like 2, we'll have a positive numerator, positive denominator, and there is my answer. So our final increasing, decreasing intervals here will be, and I'm just going to slide this over here to show you my already written out answers to save time. There it is, increasing from -1/2 to 0, and then 2 to infinity. And notice, of course, we're using those closed intervals, and we have our relative maxes and mins also listed here as well. I wanted to take the last seconds of this video just to look at the graph of the last question, because for all of these questions, a good way for you to check your answer or as an answer key for this is to just simply go over to something like Desmos and type in the equation and look at your answer. So back in our answer, we saw that it was our increasing, decreasing intervals, that the graph was decreasing, then it was increasing, then it was decreasing again, and then lastly it was increasing. So everything matches up against our sign chart. We also can see that we have minimums here, relative minimums, at -1 and 1, and they are cusps. Remember that we saw and confirmed that they were places where the derivative was not defined, and we can see that that was confirmed. At 0, however, is a horizontal tangent line, and that's because we had set the numerator equal to 0. So there's our 3 critical points, all here in black, which is, again, another confirmation of what we've done in these problems. So that's the main goal of this first derivative test, is an ability to use the first derivative to analyze what the graph is doing without actually looking at the graph that we are currently seeing on the screen. So I hope this video was helpful on top of what we learned in class today. Good luck in your work, and certainly reach out if you have any questions.